Good morning. Let's start our lecture today. Basically, in the previous classes, we've learned about second-order differential equation, right? So there are a few cases. The first case is x second plus b x prime plus cx is equal to 0. This is the constant coefficient. And homogeneous, right? In this case, what you do is to use the characteristic equation. All right, so in the previous classes, we've learned second-order differential equation with constant coefficient and homogeneous. In those cases, what you do is you use the method of characteristic equation. So when you have a Stokes term or Fox term, so this is constant coefficient and inhomogeneous. What you do is you use the undetermined coefficient method, right? So whenever you have a Fox, what you do is you guess for the for the particular solution, and then you solve the homogeneous equation using the characteristic equation, and you add all of them and you get a solution. And this is the so-called undetermined coefficient method. All right. Now, in the previous class, what we've learned on so far is also this kind of equation, right? So this is constant coefficient and non-constant coefficient. And inhomogeneous. And this is what for those equations, you have to use the Laplace transform. All right? So I repeat. For constant coefficient and homogeneous equation, you use the characteristic equation. For constant coefficient with inhomogeneous Fox, what you do is you use the undetermined coefficient method. And then for non-constant coefficient and non-constant Fox, what you do is you use the Laplace transform. All right, so now today we're going to learn a special case of this guy. But you can still use the characteristic equation method. All right, so today what we've learned is this kind of equation. Plus b x second plus cx 0. So in this case, you have non-constant coefficient homogeneous, and you can use the characteristic. All right, so but in this case, the characteristic equation is different, right? So, and this equation is called the Euler-Cauchy equation. Right. So now let us study the Euler-Cauchy equation. So this is 2.9. So I rearrange a little bit the contents, but it is the same. Right? So the Euler-Cauchy equation has the following form: at squared x second plus bt x prime plus cx is equal to 0. And you have yes. So this is the equation. All right. this is the equation. So this equation is completely different from this equation because in this equation you have t, right? So this is different from ax second plus bx prime plus cx is 0 due to t squared and t. All right? It's good. I explain again. This is the big picture, right? So whenever you do anything, you have to capture the big picture, right? So even in mathematics or physics or anything, you need to know what you are doing. So what we are doing is to try to understand how to solve second-order differential equation. The first method is the characteristic equation method. This is applied to the case when all of the coefficients are constant and you have an homogeneous force. Now, when the force is not homogeneous, you have to guess for the particular solution and you add it with the solution of the homogeneous equation. And this is the so-called undetermined coefficient method. All right? Those equations are for constant coefficient. What happens if you have non-constant coefficient? When you have non-constant coefficient, one method which is quite efficient is the Laplace transform, which is this one. All right? And then this method is powerful, but today we're gonna learn a special case of non-constant coefficient. And we can still use the characteristic method, right? So this is a subcase of what we've learned about the Laplace transform. So in this case, the equation has a very special form, and this is the so-called Euler-Cauchy equation. In the Euler-Cauchy equation, you have ax second bx prime plus cx, but the difference is here, you have t square and t, which means that this is a non-constant coefficient equation. All right, so let us try to understand how we can solve this equation. Right. So I mentioned that this equation can be solved using the characteristic equation method. All right. So coming back to the previous case. You have ax second plus bx prime plus cx is 0. So how can we establish the characteristic equation? In the previous case, where you have so this is the simplest second-order differential equation that you have. In this case, we've learned that we can solve this equation using the characteristic equation method. But the question is that, do you remember how we can establish the characteristic equation? Yes?
You said you make it like AR squared plus BR plus C
Yes.
equals 0, then you factor to find the roots.
Right, but how can we get to that equation? Right, so we know that the characteristic equation is AR squared plus BR plus C is 0, right? In one of our previous classes, I explained to you how we can reach to this equation. Right? So how can we get there? Yes?
Didn't we look for special solutions of the form x is equal to e to the RT?
Yes. Just add back of this. Right? So the key idea of getting this characteristic equation is the following. You look for special solution. We look for solution of the type x is e to the RT. All right? So we guess that the solution should be of this type, and then we plug it back to the equation. to 1, right? So now we have what? We have x prime will be, what is x prime? Yes? Yes, can you sign back the paper, please? So this x prime will be at e to rt, and what is x second? Yes?
R squared e to the rt.
Yes, can you sign back the paper, please? R squared e to rt, right? So which means that when you put everything together, so you get r squared e to the rt times a plus b e to rt plus c e to rt. This is the what you get. All right. Right. So I had I'm gonna announce the final project tonight. I'm gonna put it on Canvas. The deadline will be January 18 at 5 p.m. So I'm gonna what you do is that you have to type them on LaTeX or Word or whatever you want, and you send it to me by email. All right. So if you don't type it, I don't accept the project. Yes.
Do you mean December 18th for the deadline?
December 18th, right? Today, yes, December is in 1 month, right? So at 5 p.m. So if you don't type it, I don't accept it. If you you are late, I don't accept it, right? And you will be asked to solve 7 questions, and 7 questions are 8 questions that are easy, including those kind of things, right? So I'm gonna ask you to solve all of the questions that you've learned so far, including this guy, this last guy. And so you have to type it. This is important. You have to type it. You cannot write it by hand and take a picture and send it to me. This is not acceptable. All right? And you have 1 month to do it, which is quite flexible. And this equation will be the last questions. And the next thing is that since we don't have homework anymore, so if you have extra credit, so if you have 1 extra credit, like you answer questions in class, 1 extra credit will be counted like 1/4 point for the final project. All right. So if you answer 4 questions, you get 4 extra credit, which means that in the final you get 1 extra point. All right. So and the total point for the final exam is 25, as we discussed before in the syllabus. So if you are active in class and we don't have homework anymore, it's still counted. So there's no problem. Questions? Yes?
So you would need 100 extra points to not do the final at all.
Yes, you have to answer 100 times too. But doing the final project is easier than other questions. All right, so let us come back to this equation. So you have ax second plus bx prime plus cx. You plug x second to be r squared e to rt, which gives you a r squared e to rt. X prime you can plug r e to rt. You get b r e to rt plus c e to rt, right? Now you put e to rt as a common factor, and you see the characteristic equation, right? This is the characteristic equation. So if we can find r, we can find r such that a squared plus br plus c is 0, then ax second plus bx prime plus cx is 0, with x is equal to e to rt. Right? So instead of solving, ax second plus bx prime plus cx is 0, we find r such that a square plus br plus c is 0, and this is the characteristic equation. All right. I explain again. The idea of finding the characteristic equation in the class in this case is that you guess for a solution of this type, and you plug it back to the equation. So when you do it, at the end you're gonna get e to rt ar squared plus br plus c. This is the characteristic equation, because if you can find out so that ar squared plus br plus c is 0, then x is equal to e to rt will solve the differential equation, right? So instead of solving the differential equation, what you do is you solve the characteristic equation, you find their roots, and you put e to rt to those roots, right? And this is the key idea of the characteristic equation. Questions? Now, we're gonna go one step further, which is the equation that we have before. So Euler-Cauchy equation. So in this Euler-Cauchy equation, you have ax t squared plus b tx prime plus cx is equal to 0, right? And we want to find something similar to the previous characteristic equation. So we want to find a characteristic equation. A similar characteristic equation. All right. Right. So in this case, this is inhomogeneous, non-constant coefficient. And we still want to find a similar characteristic equation. So what I do is I apply the same trick, right? So I'm gonna. So first, we look for solution of the type x is equal to e to rt, right? And then we still have x second is r squared e to rt, x prime is r e to rt. So what equation should we get in this case? Yes?
We get a t squared r squared plus btr plus c
Yes.
is equal to 0.
Yes, can start back paper, please. Now I plug everything back into the equation, right? So I have a t squared r squared e to rt plus bt r e to rt plus c e to rt is 0, right? And now I factorize e to rt. I get a t squared r squared plus btr plus c is 0, which means that a t squared r squared plus b tr plus c is 0, right? So the first guess is that we look for similar type of solution. X is e to rt, and we plug it back to this equation. What we get is a t squared r squared e to rt, and here you have b tr e to rt plus c e to rt. So I put rt outside, I get a t squared r squared plus b tr plus c is 0. So is it that can we take this as a characteristic equation? Can this be a characteristic equation? Right? So I explain again. In the previous case, you don't have t squared and t, right? This was the constant coefficient equation. What we did is we plug x is e to rt, I is a constant. And then we found an equation. In this case, we do the same. We plug x to e to rt, but the difference is here I have t squared and t. And finally, I have this equation. Can this be a characteristic equation? Yes?
Would it be possible for us to consider TR as our variable? Because last time we factored, of course, with respect to R, because we were searching for R. Would it be possible to search somehow for T times R?
That is a good idea. Can you stand back the paper, please? So this is a good idea, but let us see if this is working. So if we put R tilde to be RT, right? We get A R tilde square plus B R tilde plus C 0. All right, so this is a quadratic form. Right, suppose that we can find, suppose that we solve, suppose that one is a solution. Is e to R1 tilde t a solution of, I don't know this Euler quotient. Right? So I followed the idea of 8 and 9. So what we did is that we put R tilde to be RT, we get an equation AR squared plus B, AR tilde squared plus B R tilde plus C 0. Suppose that you have a solution for this, which is a constant. Sorry, this is not, so this is the solution, which means that which means that yes. Sorry. So if we put R tilde to be RT, what we have is AR tilde square plus BR tilde is plus C is 0. This one you can solve it because it's a quadratic form. You can use the delta, right? Suppose that you can find R1 tilde, which is the solution of this equation, is ER tilde 1 over t, because we have to divide by t, right? And then you multiply it with t. Is it a solution of this equation? Of the original equation? Right, so you put R tilde to be RT, right? So you solve this equation, but you have to go back to R because R is what we want to solve. So you have to divide that by t. And then after you have the R, you multiply that with t again. Is it a solution of the equation? So I give you a special case. A is equal to 1, B is equal to 0, and C is equal to minus 1, right? So in this case, what you get is t squared, r squared, plus, this is 0, so you have minus 1, 0, right? So I consider a special case. A is 1, B is 0, C is 0. So I have A is 1, B is 0, C is minus 1, right? So then I plug it to this equation. I'm gonna get R squared, T squared, minus 1 is 0. Now I'm gonna put R tilde to be TR. So I have R tilde squared minus 1 is 0. Right? I can solve this equation. One solution is R tilde 1 is 1, right? But R tilde is TR, so in this case, R should be 1 over T. And so I plug it back to the form of the solution, right? X is equal to RT, which is E1 over T times T. Is it a solution of the equation? The equation should be what? The equation is t squared x second minus x is 0. Is this solution? Why?
Her or me?
You.
Oh, well, if we plug that back in as x double prime would come to 0 because it's a constant. X prime would also be 0 because the derivative constant is 0, but it's not a solution because you get c times e, which is not equal to c.
Right. So you lose everything here. Right? So can you stand back paper, please? So if you do it this way, right? If you do it this way, so this one, so what is e tilde over t? This gives you e tilde 1, which is a constant. Right? Finally, the solution you get is a constant, which is not a solution of the original equation. Right? So in this special case, what we have is what? What do we have? A is 1, b is 0, c is minus 1. So this is t. So you have t x second, t square x second minus x is 0. So the equation that you get here is t square r square minus 1 is 0. And you put t tilde to be tr, then r tilde square minus 1 is 0. So r tilde should be 1. In this case, the r will be 1 over t. When you multiply by, the solution is e. And e is not a solution of this equation. Right? So e is not a solution. Because when you plug it back, you have t squared is second minus e is 0. So this is 0. So minus e is not 0. Right? So this is not a good way to find a characteristic equation. Right? So which means that this type of solution is not good. Right? So any suggestion for the type of solution that we should look for? If you try exponential and this doesn't work, what is the next step? If you try to look for a solution of the exponential type and this doesn't work, and you want to guess the next step, so what is the next solution that you guess? Yes?
Maybe natural log of e.
This is too far, but this is good, but this is too far. So going from exponential to log is too far. What is the middle step? Yes?
Could you multiply the exponential by a polynomial?
You replace it by a polynomial, right? It's clear? Right, so of course in this case you cannot use the previous trick. So let me try to find a characteristic equation. So first we look for the solution of the type exponential. It doesn't work, right? So second we try x to be to the t. T to r, sorry. This is part, right? So this is how Euler try it. So he knows in advance that, okay, for this equation, for the constant coefficient equation, you have exponential. But people don't know how to solve this equation. E t squared x second plus b t x prime plus c x is 0. So Euler and Cauchy then propose the second type of solution, the second type of guess, right? So x should be t to r. So let's try if this works. So what is the first derivative of the polynomial? Yes?
Rt to the r minus 1.
Yes, can you say the back please? T minus 1. Right? So what is the second derivative of this guy? Yes?
So it'd be r squared minus r times t to the r minus 2.
Yes, can you say the back paper please? So this is r minus 1, t minus 2. Right? So, of course, for the first solution, it doesn't work. And Euler and Cauchy proposed the second type of guess. So he guessed that the solution, they guessed that the solution is of the type polynomial. So x is t to the r. So x prime will be t minus 1, and then x second will be r minus 1, t r minus 2. And so let us plug them back into the equation. So you have a t squared mx prime plus b tx prime plus cx 0. So this one I'm gonna replace it by a t squared minus 1 t minus 2 plus b t minus 1 plus c ti is 0. All right? Right, so you're gonna plug this solution, this solution into the equation. So x second will be r minus 1 t to r minus 2. X prime will be r minus 1 and x will be t to r. Can we simplify this? Yes?
I guess you could factor out a t to the r, so then you would be left with a t
Yes,
to the
yes.
negative t.
Can you sign by of this? So this guy and this guy, you get t to the r. And this is also t to the r, so you have a r minus 1 t to the r plus b r t to the r plus c t to the r. Right? I can factor t to the outside, so I have a r minus 1 plus b r plus c is 0. All right? That's good. Right, so I explain again. You try the first guess, you don't get anything. You try the second guess, which is a genius idea of those people back into the 17th century. So what you get is that when you plug this second derivative here and this first derivative here, you get a t squared r minus 1 t r minus 2. The t squared and the t r minus 2 can be combined to t to the r. And then the t r minus 1 can be combined to the t to the r. So you can factor t to the r outside and you get this equation. Right? So then you have a r minus 1 plus b r plus c is 0. Right? And this is the new characteristic equation. Right, so you have a r squared minus a r plus b r plus c is 0. And this is a r squared plus b minus a r plus c r is 0. This is the characteristic equation. All right? Questions? So this is a characteristic equation in the sense that if we can find, we solve a r squared plus if r1 satisfy a1 squared plus b minus a r1 plus c 0, then a r1 a t squared r1 to the t to r1, sorry, t to r1 second plus b t r1 prime plus ct is 0. Right? So this is a characteristic equation because if you can find a number that solve this quadratic form, right? If you can find r1 such that a r1 squared plus b minus a r1 plus c is 0, then a t squared plus t r1 second plus bt t r1 prime plus ct is 0. And this is a solution, which means that tr1 is a solution. All right? Questions? And this is the characteristic equation that you have in this case. It's clear? I explain again. So this is the Cauchy-Euler equation. This is a non-constant coefficient second order differential equation, right? but we want to solve it by the method of characteristic. So how can we solve it? First, we look for exponential, and it's not work. So the next step is that you try to look for a solution of polynomial type. So you find a solution of the type x to the r. So r is a constant that you have to find. You plug everything into the equation. The magic is that after you plug everything into the equation, you found ar squared plus b minus ar plus c is 0. This equation doesn't depend on t. And this is the meaning of a characteristic equation, right? So this equation doesn't depend on t. Right? So the key idea of the characteristic equation method is that you reduce a differential equation in a variable t into an equation on constant only, right? So your final task is to find a constant that satisfies this relation, which is independent of t, right? So the idea of the method, the key idea of the method of characteristic equation is that we reduce an equation, a differential equation in t. To an equation, to a characteristic equation which is independent of t. All right. So the key idea of a method of characteristic equation is that first you have a differential equation. This differential equation is an equation of the variable t. This is the trouble, right? So, but the characteristic equation method allows you to reduce that to an equation which is independent of the variable t, and this is what we did, right? So we find a solution of the type t to the r. You plug it back to the equation, you get this equation. This equation is an equation for the constant r, and you can solve it. And you find the r explicitly, and then you plug it back, you get t to r1 is the solution, right? Questions? It's clear? Right, so to summarize, the characteristic equation is ar squared plus b minus ar plus c is 0. Right? Questions? Example. Solve the equation. T squared x second plus plus 3t x prime plus 5 0 5x. Right, so plus minus 2x. All right, so now let us try to solve this equation, right? So you have t squared x second plus 3tx prime minus 2x is 0. The first thing I want to know is what is A, what is B, what is C? Yes? can say it back paper please. A is 1, B is 3, C is minus 2. Right? And the characteristic equation. So what is the characteristic equation in this case? Yes?
R squared plus 2R minus R.
Yes, can you say it? And the back paper please. So you have R squared plus B minus A, so this is 2R, and C will be minus 2. Right? So I want to know the two, so this equation has two roots. What are the roots of this equation? Yes?
-1 minus square root
Yes, can you say it back paper please? So to compute the root, first you compute the delta, right? So this is 2 squared minus 4 times minus 2. So this is 4 plus 8, and this is 12. All right? The delta will be 2 squared minus 4 times this guy, which is 4 plus 8, and this is 12. So the two root will be 1, 2 is minus 2 plus or minus the square of 2, 12 over 2, and this is minus 1 plus minus 2 plus or minus 2 square root of 3 over 2, and this is minus 1 plus or minus square root of 3. All right? Is it good? I explain again. All right? So this is the equation that we have. This equation has a different characteristic equation. So the characteristic equation will be R squared plus 2 minus 2. So this is A, this is C, and this is B minus A. Right? A is 1, B minus A is 2, and C is minus 2. Right? Now I have two roots for this equation. Why? Because I computed delta. This is 2 squared minus 4 times minus 2. This is 4 plus A, and this is 12. So I have minus 2 plus or minus square root 12 over 2. This gives me minus 1 plus or minus square root 3. Right? So this is the R1. Minus 1 plus square root 3 minus 1 minus square root. Right? So from theory that we explained before, we have two solutions, right? What are them? What are they? Yes?
It will be t to the r1, so t to the negative 1 plus root t, and then t to the negative 1 minus root 3, and we can write those two together because we know the linear combination of two solutions is also solution, so we can write it as our general solution as x equals a constant times that first solution plus the second constant times the second solution.
Yes, can you sign the back of the paper, please? So from the theory that we have before, we have one solution which is x1t will be t to the r1, which is t to the power minus 1 plus square root of 3, and x2t is t to r2, and this is t minus 1 minus square root of 3, right? So from the theory, we know that, okay, if you find an r1 that solves this equation, t to r1 will be one solution. Similarly, if you find r2, which is a solution of the same equation, then this is also a solution, right? Right. So the general solution should be xt is c1 x1t plus c2 x2t, and this is c1 t to the power minus 1 plus square root of 3 plus c2 t power minus 1 minus square root of 3. Right? So we know that if R1 solve this equation, then T to R1 solve the differential equation. And if R2 solve the characteristic equation, then T to R2 solve the characteristic equation. Now, because this is the linear equation, you can take linear combination of the two solutions, right? So you can multiply x1 with c1 and x2 with c2. This is also a solution. Right, but I mentioned linear. I mentioned that this is okay. So to explain this clearer, so because x1 solve the equation, right? So you have a t squared x1 prime plus bt x1 prime plus c x1 is 0, and then you have a t squared x2 prime bt x prime plus c 0, right? So in this case, x1 is this guy, x1 is this guy, and x2 is also this guy, right? So I want to say that xt is c1 x1 plus c2 x2 is the solution. Right? Why? First, by the theory, we said that if I can find an R1 that solves the characteristic equation, then T to R1 is the solution. And if I can find R2 such that R2 solves the characteristic equation, then T to R2 solves the equation. Now, I said that if you linear combine them, you get a solution of the equation. Why? So if I have x1 that satisfies this equation, and I have x2 that satisfies this equation, then c1 x1 plus c2 x2 also satisfy that equation. Why? Yes?
If you were to take your x as x1 plus x2 and put it back into that original equation, you could factor out terms in order to get those two equations, and because both of those are equal to 0, 0 plus 0 is also equal.
Yes, can you say it back, please? Because when you plug it back to the equation, you get 0, right? Right, so so in this case, let me focus on the case that we have in hand. So you have 1, 3, then here you have -2. Right, so now I'm gonna plug this form into the equation. You have 1x t squared x prime plus 3t x prime minus 2x. So this gives you t squared. You have c1 x1 plus c2 x2 second plus 3t c1 x1 plus c2 x2 prime minus 2 c1 x1 plus c2 x2, right? And I said that this is 0. So can someone explain it clearer for me? Why is it 0? I know that I know this is 0, right? Because this is one solution. I know that this is also 0, because this is the second solution. But I said that if I combine them, c1 x1 plus c2 x2, and I plug it to the equation, I also have 0. Can someone explain it clearer to me? Yes?
Expand t squared into each respective term, and then 3t, and then -2 in each component of each equation, and they combine together.
Yes, can I say it back of this? So this is a brilliant idea. So you have t squared, this guy gives you c1. This guy gives you c1 x1 prime, right? And then this guy gives you t squared c2 x2 second, right? So this guy gives you c1 t squared x1 second, because c1 is a constant. So this guy gives you c2 t squared x2 second. This guy gives you c1 3t x1 prime. This guy gives you c2 3t x2 prime. This guy gives you minus c1 times 2x1, and this guy gives you minus c2 2 times x2. Right? You just expand it. So the first guy gives you c1 t square x1 second. Second guy, the first guy also gives you c2 t square x2 second. The second guy gives you c1 3t x1 prime, and then you have c2 3t x2 second prime, and then here you have minus c1 2x1, and here you have minus c2 2x2, right? And then you combine them. So this circle combined with this circle, and this rectangle combined with this rectangle and with this rectangle. So when you combine all of the circles, you have t square plus c1 x1 second plus 3t x1 prime minus 2x1. And then when you combine all of the rectangle, you have t square x2 second plus 3t x2 prime minus 2x2, right? First you expand them, and then you have all of the circle. The circles are for x1. The rectangles are for x2, right? So and then you combine the circle together, like Trevor said, you have c1 t square x1 second plus 3t x1 prime minus 2x1, and then the other guy is c2 t square x2 second plus 3t x2 prime minus 2x2, and this is 0, and this is 0 because of this, right? So this is 0 plus 0, and you have 0. Right? So if you find two solutions, you can linearly combine them. Questions? It's clear? Right, so let us go to the theory. Any questions on this so far? So again, this is the calculus equation. You have a r squared plus b minus a r plus c r is 0. The delta will be b minus a squared minus 4ac. Case number 1. Delta is positive. The characteristic equation has two roots. R1 will be minus b minus a plus square root delta over 2a, and R2 will be minus b minus a minus square root delta over 2a. And we have two solutions. So the x1 will be t to the r1, and x2 will be t to the r2. General solution is xt is c1 x1 plus c2 x2, and this is c1 t to r1 plus c2 t to r2. Right? Questions? So I explain again. The first case is the easiest case. You have the Euler-Cauchy equation. A t x second plus bt x prime plus cx is 0. This equation has a characteristic equation that we derived before. This is ar squared plus b minus a plus c b minus a r plus c is 0. Right? So the delta will be b minus a squared minus 4ac. There are three cases. The first case, delta is positive. The characteristic equation has two roots. The first one is of this type, and the second one is this one. So you have two solutions, right? T to R1 and T to R2. Because this is a linear equation, you can linearly combine them to get a general solution. You have C1, T to R1 plus C2, T to R2. Questions? It's good. Right, so let us go to one more example so that you example find the general solution of 2t squared x second plus 7tx prime minus 3x is equal to 0. Right. So in this example, what you have to do is to find the general solution of 2t squared x second plus 7tx prime minus 3x is 0. Of course, you can solve this equation using Laplace transform, but this is more complicated and this is easier, right? Because this is straightforward. You have all of the formulas. Solution. So I want to know what is A, what is B, and what is C. Yes?
2, 7, and negative 3.
Yes, inside back paper, please. So A is 2, B is 7, and C is minus 3. All right? So the characteristic equation. So what is the characteristic equation? Yes?
It would be 2r squared plus 5r minus 3 equals 0.
Yes, inside back paper, please. So you're going to get 2r squared plus 5r minus 3 is equal to 0, right? So because this is A, this is B minus A, and this is C. Right, so you use the formula, you see that the characteristic equation is 2r squared plus 5r minus 3 is 0. So what are the two roots of this equation? So what is the delta first? Yes? What the delta is 7? The delta is 7, no? 49. Right, so this is delta is 5 squared minus 4 times 2 minus 3. This is 49. So you meant 7 squared, right? Can you sign it back paper? Right, so this is 7 squared. Right, so the delta will be 25 minus 4 times 2 minus 3, and this is 49. And so I want to know the two roots. Yes?
Negative 3 and 1.
Yes, you can sign the back paper, please. So you have minus 5 plus or minus 7 over 2 times 2. So let me do it separately. So the first one is minus 5 minus 7 over 2 times 2. This is minus 12 over 4, and this is minus 3. The second one will be minus 3 plus 7 over 2 times 2, and this is 1/2. Right? What are the two solutions? Yes?
So the two solutions are t to the negative 3 and then t to the 1/2.
Yes. Can you sign back paper, please? So the first solution will be e t to the power minus 3, and the second one will be t to the 1/2. What is the general solution of this? Yes? Yes?
C1 t to the negative 3 plus C2 t to the 1.
Yes, can you sign back paper, please? So x will be c1 t to the power minus 3 plus c2 t to 1/2. Right? So is it easy, right? Questions? It's good. So basically, this is the first case. First case is always the easiest case, like what we see in the constant coefficient differential equations. Now, let us go to the next step when delta is 0. Alright, so again, you have at squared as second plus btr x second x prime plus c x is 0, right? So in this case, you have ar squared plus b minus a plus c is 0, right? So case number 2, the delta is b minus a squared as for ac. Case 2, delta is 0. So when delta is 0, what happens with the characteristic equation? When delta is 0, what happened to the characteristic equation? Yes?
It's a double root.
Yes, inside back paper please. So the characteristic equation has a double root. Right, so you have r is minus b minus a over 2a. Right, so the characteristic equation in this case has a double root. So one solution should be is x1t is t to the r, and this is t to the power minus b minus a over 2a. Right? So can you suggest to me the second solution? So to come, yes?
It'll be like RT to the R.
RT to the R. I is a constant already, right? So when you multiply that with R, it's still the same. Right? I is this constant. So RT to the, so you mean RT to the R like this?
Yeah.
It is still this one, right? Because I is a constant. Yes?
Will we multiply our solution by t, because that's what we did last time with the exponential with the double root?
So what you suggest is to multiply this with t. So this gives you t to r plus 1. I don't know. Any other suggestion? Right, so remember that in the other case, right, so for ax second plus bx prime plus cx is 0, right, so you, the characteristic equation is br plus c, 0, right? So if the delta is 0, you have 0, and this is b squared minus 4ac. So when delta is 0, you have one root, which is minus b over 2a. And then this gives you x1 is e to the rt, x2 is e to the rt times log t, times t. Right? In the previous case, in the constant coefficient case, you have ax second plus bx prime plus cx is 0. And then the characteristic equation is ar squared plus br plus c. The delta is, when the delta is 0, you have one root, which is minus b over 2a. X1 will be e to rt, and x2 will be multiplying x1 with the t. Any suggestion for this case? Yes?
Because in our second solution to that one, we went from an exponential, we multiply it by polynomial, which you can kind of think of as going down in terms of your function's power. Will we multiply our function by something less than a polynomial, so
What is it?
something like a logarithm?
Yes, and it's had a bank paper this. So this is just go down one more scale, right? So x2t will be x1t times log t. And this is how you remember the two cases, right? Right? So here you have exponential, you go to polynomial. And then the second solution, you multiply it with t. And for this case, you just go down one more scale, which is log. Right? So this is how you remember it. Right, so the first solution should be this guy, and the second solution is the first solution multiplied with log t. And how do you remember it? You remember that, okay, for the previous case, the solution is exponential, and you replace exponential by the polynomial, right? In the previous case, you have t. Now you replace t by log t. Right, so how to remember? Star, and this is Euler Cauchy. So you go from star to Euler Cauchy by replacing e to rt with t to the r, and then you replace t with log t. Right? It's good. So how do you go from the classical case, the constant coefficient case, to the Euler Cauchy case? You just replace exponential by polynomial, right? And then the t by log t, right? So here you replace t by log t. Questions? Right. So if there's no questions, let us go to one exercise. And do you remember how we can find the t? That x2 is x1 multiplied with t in the previous case? In the constant coefficient case, when you have a double root, the first solution is exponential, the second solution is exponential times t, right? Like what I wrote there. Do you remember the proof? How do you go from x1 to x2? There's a name for the method. What is the name of this method? First one is reduction. What is the next? Yes?
Reduction of order.
Yes. Can you send my paper, please? Right? So to go from x2 to x1, you do what? You do reduction of order. Remember that? So you have x1 is e to the rt, and x2 is t times x1. So how do you find this t? You consider w is x2 over x1, right? And then you write x2 as w times x1, and you plug this back to the equation. You have w x1 second a plus b w x1 prime plus c w x1. 0, right? And finally, you find that x1 satisfy w prime satisfy our first order equation. Right, so this is how you found x2, right? In the previous case, you have the first root. In the previous case, you have a double root for the characteristic equation. So the first solution should be e to rt, and the second solution. To find the second solution, you suppose that w is x2 over x1. Then x2 is w times x1. You plug everything back into the original equation. Then this is the second order equation. But when you plug it back to the equation, you get that w prime satisfying a first order differential equation. So you reduce the order from second order to first order, right? So now we have to exercise. So you have t squared x second minus t 16 is 0. Right, so this is the equation that we need to solve. So what is A, what is B, what is C? Yes?
1, negative 7, and 16.
Yes. Let's add back paper, please. 1 minus 7 and 16. What is the characteristic equation?
R squared minus 8
can side back paper, please. So you have r squared plus 8r plus 16 is 0. Right, so this is a is 1, b minus a is 8, a minus b, what? B minus a is minus 8. And this is c 16. Right? Right, so what is the double root of this equation? Yes? 4. Yes, can you sign back paper, please? So this equation is minus 4 squared is 0, right? So which means that you have one double root 4, which means that what are the two solutions of this equation? Yes?
T to the 4.
And?
L and T to the 4.
Yes, can you sign back paper, please? So in this case, you have x1 is t to the 4 and x2 is t to the 4 log t. Right? What is the general solution of this equation? Yes?
C1 T to the 4 plus C2 L T to the 4.
Yes, so you have xt is x1, c1 x1 plus c2 x2. And then this is c1 t to the 4 plus c2 t to the 4 log t. Right? Questions? So this is there's an analog between the previous one and this one. The analog is that whenever you have t over there, you replace it by log t. Right, so let us go to any questions on this? It's clear? Right, so let us go to the next case when delta is negative. Case number 3, delta is negative. So what happens when delta is negative? You have two roots. What are they? Yes?
They'll be imaginary roots, so we'll have, they'll be complex, so they'll involve I, so it will be negative b plus or minus I times the square root of delta over
Yes, you
2.
can stand back here, please. So you have R1 and R2 will be minus b minus a, still plus or minus delta, right? Over 2a. But this delta is negative, right? So because delta is negative, the square root of delta will be I square root the absolute value of delta, right? So in this case, you have minus b minus a plus or minus square root of I through delta over 2a. Right? I explain again. So in this case, the delta is negative, so the delta, square root delta will be I times the square root of the absolute value of delta. So the two roots will be minus b minus a plus or minus square root of delta over 2a. And this is minus b minus a plus or minus square root of delta over 2a. Right, so what is x1? Yes?
T to the negative b minus a plus or minus I squared delta over 2.
Right, can you stand the back paper, please? So x1 is still the same, right? T to the r1. All right? So this t to the r1 will be t to the minus b minus a plus or minus I square root of delta over 2a. This is complex number, right? So we have trouble, but it's fine. So we have t power minus 2a over 2a, which is the real part. But so let me consider plus first. So you have I t to the square root delta over 2a. What is this t to the I square root of delta over 2a? Right? So by the theory, this is still the solution. Right? So t to the r1 is still the solution. When I plug r1 there, I have minus b minus a plus square root of I square root the absolute value of a over 2a. Here you have the real part and you have the imaginary part. The real part will give you polynomial, like in a classical sense, there's no problem. The imaginary part will give you some trouble. So how can I define t to the power I of something? Yes?
Is it t to the cosine?
Remember the previous case. So in case number 3, right? In case number 3, in the previous equation, you have ax second plus bx prime plus cx is 0, right? So you have ar squared plus br plus c, 0. And then the delta is negative, so you also have 2 root minus b over 2a plus or minus I square root delta over 2a. Right? So when you have e, so you take e to the 1t, this gives you e to the power minus b over 2at plus I square root delta over 2a t. And then the first one gives you e to the power minus 2a, and the second one gives you this guy. What did we do with that imaginary guy? Yes?
Didn't we change, it became that e to the I square root of delta over 2a, we changed that, that became cosine of square root of delta over 2a t.
We didn't change. We use a formula.
Oh.
What is the name of the formula?
Euler's form?
Is what?
Euler's?
Euler. Yes, can you say it back to paper, please? Right? So we have a formula called Euler formula, which is the following. So Euler formula. So you have e to the I theta will be cosine of theta plus I sin of theta. Alright, so this gives you e to the power minus b to 2a cosine of square root of delta over 2at plus I sinus of square root of delta over 2a t. This is t. Right? So, in the previous case, you remember that when delta is negative, you also have 2 complex roots. The first one is minus b over 2a plus I square root of delta. So the real part, you take it to be exponential. The imaginary part, you use the Euler formula. The Euler formula is the following. E to the I theta is cosine of theta plus I sinus of theta. Right? Right. So we're going to do something similar here. So the Euler formula is one of the most beautiful formula in the world. Why? Because when you replace this theta by pi, what do you get? This is not really related to this one, but I just want to comment that this is one of the most beautiful formula. Because when I replace theta to be pi, what do I get? Yes, can you say back the paper, please? I get cosine of pi plus I sinus of pi, and this is minus 1. So I have e I pi plus 1 is 0. So in this formula, you have the e, the pi, the 1, and the 0. So you have everything in mathematics in one equation, right? And this is why this is called the most beautiful formula in mathematics, because you have everything. The number I, the number pi, the number 1, and the number 0. All right? So in this setting, we use this formula, the Euler formula. You have e to the power minus b over 2at e to I square root of this guy. So this guy is the standard exponential. This guy, you use Euler formula. I said that for this case, you're going to use the same kind of thing. How can I do it? We need the exponential, right, to use the Euler formula. But here you have a polynomial. Yes? Right. Can you say at the back of the paper, please? You want to use this Euler formula, but here you have a polynomial. So how can you do it? You just change t to e to the log t. Right? So this gives you t to the power minus b over 2a. E to the log t I square root of delta over 2a. And this gives you t to the power minus b over 2a is to the I square root log t. Right? So to use the Euler formula, the trick is then to change t to e to log t. We're going to continue on Tuesday. So have a nice weekend.